Okay, let's look at some neutralization reactions here. So again, I've got my list of strong acids and bases at the top. So these are all my strong acids, and these are all my strong bases. And I'm telling you in this problem that they're strong acid-base neutralization reactions, but you should be able to recognize that whenever you make a solution of both an acid and a base, they can't both exist simultaneously, especially if they're strong acids and strong bases. They won't both exist in solutions simultaneously, so a neutralization reaction will happen. This is kind of like if you mix a hot and a cold drink, you don't have both hot and cold present simultaneously. The final temperature is some mixture of both, and that's what's going on here. So a general workflow for these types of problems is to calculate the moles of acids and base, and then calculate any excess of either of them, and then you want to convert back to concentration of base or acid at the end. So we work in moles of acid and base because we're looking at a reaction. We're looking at reaction stoichiometry specifically. So in the following problem, we're looking at HCl plus sodium hydroxide, and that's going to make water and sodium chloride. And you'll note that the stoichiometry for this is 1 mole of HCl for every mole of sodium hydroxide. So if that stoichiometry is different, it's likely that it's 1-to-1, but it's not always true. If the stoichiometry is different, for example, if you're using calcium hydroxide or barium hydroxide or something, there's a little bit more work you have to do. But this gives you a general workflow for working on these problems without talking about the exceptions. So step 1 is calculate the moles of acid and base, and that's because our reaction is written out in terms of moles. So typically for these types of problems, you're given volumes, 30 milliliters of a particular concentration of HCl and 10 milliliters of particular concentration of sodium hydroxide are mixed together to form one larger solution. And it wants to know what the pH is of that final solution. But before we can get to the pH, we have to figure out what reaction has happened there. And so step 1 is just to take and convert your acid and your base into moles. And that's easily done by just multiplying times the volume. So I take the concentration, I multiply it times the volume, but make sure that the volume is in terms of volume. So I'm looking at HCl here. So 0.1 times 30 times 10 to the minus third gives us, actually, let me write it out not in scientific notation because I think that'll make this next part a little easier. So I'm having calculator mishaps over here. Okay, there we go. So we end up with 0.003 moles of HCl. And since this is a strong acid, that is going to be equal to the moles of H plus that I have. So that's my acid concentration. If I look at the base concentration, it's the same calculation. So here, I've generously given you the same concentrations, just to keep things simple. And so we have 0.001 moles of sodium hydroxide, which is equal to 0.001 moles of hydroxide. Okay, so step 2 is to figure out how much excess acid or base you have there. And so that is done by looking at these concentrations. So you won't have H plus and OH minus existing simultaneously in solution. They are going to annihilate one another. So you have less hydroxide here than you do acid. And so our total concentration at the end of the reaction, at the end of the neutralization reaction, once this and this have reacted together, I will have 0.002 mole of H plus and 0.000 mole of hydroxide. And that is calculated just by subtracting H plus minus OH minus, or, oops. So moles of H plus minus moles of OH minus. In this case, gives you your remaining moles of H plus. I don't like the way that sounds. But yeah, it's moles of H plus minus OH minus. So we have excess acid here. It's always this, maybe I should write this. Never a good place for it, I'm just going to delete it. But in order to calculate this number, 0.002 moles, all I do is I take the larger number and subtract the smaller number here. And that gives me my final concentration of H plus there. And then since this is a strong acid problem, in part 3, all we want to do is make sure that we're in concentration units. So pH is a measure of hydronium concentration. Moles is not a concentration, right? That's a method of counting that tells you the number of molecules of H plus you have. Concentration you have to divide by some volume. And so here the volume that we're going to divide by is going to be the total volume in our final solution, which is 30 mils, and 10 mils have been combined, so we have 40 mils. And so we take 0.002 moles of HCl and we divide it by 40 times 10 to the minus third liters, and that gives us 0.05. Right, 0.005 molar H plus. Let me double check that. Yeah. Okay. So then we want to know what our pH is, so we just take the negative log of that number. And we end up with a pH of 1.3. So this last part, where I'm converting back into concentration units, is because pH is expressed in terms of concentration. In this first part, where I'm working in moles, it's because we're dealing with reaction stoichiometry, and we're asking ourselves basically how much, in this particular problem, it's how much HCl is left over after I react it with a certain amount of sodium hydroxide. And my recipe for understanding that is expressed in moles. So you want to convert to moles. So in step 1, we calculate moles. In step 2, we calculate the excess moles of either the acid or the base. And then in step 3, we convert back to the concentration of acid or base. And that's what we can end up using to calculate pH. Okay, let's skip the middle part here and come to this bottom part. So in the bottom part, we've got 50 milliliters of hydroxide and 30 milliliters of HCl, and they're both 0.1 molar. And so we're going to follow that same workflow that we followed at the top. First, we're going to calculate the number of moles of HCl. So I'm using, this is the same, so it's 30 mils of HCl and 30 mils of 0.1 molar HCl. So that's the same for both. So it's that much HCl, which I know is going to be equal to the number of moles of H plus. And then we need to calculate what our concentration, or the number of moles of sodium hydroxide is that we have. And so that's just the same calculation that we did in the last part, which is 0.1 mole per liter. And we're going to multiply it times 50 times 10 to the minus 3 liter. And we get 0.005 moles of sodium hydroxide, which is equal to 0.005 moles of hydroxide, because it's a strong base, so they're equal. So I've got, now I'm looking at, I've got this much acid, I've got this much base, and so I just want to add those two numbers together, or subtract the smaller number from the larger number, and I can see that I have excess base here because I have more of it. So the 0.003 moles of H plus is going to react completely with 0.005 moles of OH minus. And I'm going to have, at the end of this, so in the second part, I'm just going to have excess base. So this part up here, we had excess acid, right? And so in the bottom part, we have excess base. And so what is our, how much excess base is just the amount of base that we started with minus the amount of acid that we added. And so we end up with 0.002 moles. Let's call it what it is, OH minus. And then finally, in the third step, we want to back that into whatever the final concentration is. So here we took 30 mils and we added it to 50 mils, so we have 80 mils total. And so we end up with 0.005 moles divided by 80 times 10 to the minus 3 liters. But be careful here, because remember, here we have excess base. And so what we've calculated is not the hydronium concentration, but the hydroxide concentration. And so we want to calculate the pH. So we could calculate the pOH, which is the negative log of the hydroxide concentration, which is negative log of 0.0625. Which is 1.2. Which means our pH is 14 minus the pOH, which is 14 minus 1.2, which is 12.8. Okay. So this is a general workflow for if you have excess base, which is the situation here, is excess base, or excess acid, that's how you work it. In the middle part here, you notice this is a special situation where I have some amount of acid, some amount of base and acid, and they're exactly equal. So I have 30 mils of 0.1 molar HCl. So if you wanted to go through the first part, what you'd find is that the moles of H plus is 0.003, and moles of OH minus is also 0.003. And so at the end of the reaction, I have, like in step 2, I have 0 mole H plus and 0 mole OH minus. So how do I calculate the pH? Because, you know, we need to know the H plus or the OH minus concentration in order to calculate that. Well, if I have no H plus or OH minus present from either of them, the pH of pure water dominates. So pH is just going to be equal to 7. So this is when you're at equivalent amounts of acid and base. For strong acid, strong base, that's the simplest situation. Your pH ends up equaling 7. And that's just because I don't have acid and I don't have base there. And so I'm not expecting the solution to be acidic or basic. It's just going to be neutral. And so that's how that works. So you can have a situation where it's excess acid, excess base, or the exact amounts are equal to one another, in which case your pH is just equal to 7.